Hi, my name is Trinity, and today we're going to be going over periodic trends. So in this video, we're going to be going over question 2 in your pre-workshop. Before we get started on the actual question, I want to pull up the combined graph we made at the end of the previous video. And if you remember, our combined graph shows the ionization energy and electron affinity of the row 3 atoms. If you look at question 2, you can see that it refers to another graph, and here it is. And this graph shows the actual ionization energy and electron affinity of the row 3 atoms. So looking at our two graphs, you can see that there are definitely some similarities. For example, in both cases, the ionization energy is greater in energy than the electron affinity, and there's a general upward trend in ionization energy and electron affinity as atomic number increases. However, you'll also notice a few differences. For example, you can see that there are certain spots in the graph mentioned in question 2 where the ionization energy and electron affinity decrease. For example, over here, you can see that aluminum has a lower ionization energy than magnesium, and sulfur has a lower ionization energy than phosphorus. And very noticeably, you can see that argon has a much lower electron affinity than chlorine. And the reason behind these differences is because there are factors beyond Z effective which affect ionization energy and electron affinity, and we only considered Z effective when making our combined graphs. So let's take that into account when we do the rest of question 2. So for part A of question 2, it asks us why the electron affinity of chlorine is larger than the electron affinity of argon. So the first thing we should do for a problem like this is pull up a periodic table and locate the elements in question. And once you do that, you should draw an energy diagram of each element. So let's make our first diagram of chlorine and our second one be of argon. Looking at our periodic table, we can see that the electron configuration for chlorine is this. And argon's electron configuration would be this. So let's use those electron configurations to fill in our energy diagrams. Okay, so if you look at part A, you can see that we're being asked for the electron affinity. And if we remember, the electron affinity is the amount of energy released when a new electron is added. So let's see where that new electron would be added for each element. So it'd be added here in chlorine and be added here in argon. And if you remember, the electron affinity is larger when the electron enters a lower energy level. And if you look at chlorine, you can see that the new electron enters the third shell in chlorine, but it enters the fourth shell in argon. And since the third shell is lower in energy than the fourth shell, then chlorine has a larger electron affinity than argon. To summarize it, we can call this the full shell effect. And the full shell effect says that an atom with a full shell has a low electron affinity because the new electron enters a higher shell. So the answer to part A is the full shell effect. And now let's do part B. So part B asks us why the ionization energy of phosphorus is larger than the ionization energy of sulfur. So we start off the same way by pulling up a periodic table, and then we draw an energy diagram of our elements using the electron configurations, which for phosphorus is this, and for sulfur is this. And using those electron configurations, let's fill in our energy diagrams. So part B is asking for the ionization energy, and if you remember, the ionization energy is the amount of energy it takes to remove the outermost electron. So the outermost electron in phosphorus would be this electron, and the outermost electron in sulfur would be this electron. So now let's look at the subshells where the outermost electron resides. So in phosphorus, the outermost electron is in the 3p subshell, and you can see in this 3p subshell that all 3 electrons occupy their own orbital. Now, if you look at sulfur, you can see that the outermost electron also resides in the 3p subshell, but then in the case of sulfur, 2 of the 4 electrons are sharing an orbital. Now, if you remember, electrons are negatively charged, and since like charges repel, these 2 electrons are repelling each other, and this leads to destabilization. And destabilization results in the entire 3p subshell in sulfur to have a higher energy level. So let's write that down. The 3p subshell in sulfur is destabilized, which means it is higher in energy, and remember, when something is higher in energy, it has a lower ionization energy. So this explains why phosphorus has a larger ionization energy than sulfur. We can summarize all this by calling it the half-shell effect. And the half-shell effect says that a half full shell is extra stable because there is no same orbital electron-electron repulsion. So the answer to part B is the half-shell effect. And now you're done with question 2. I hope this video helped. Thank you for watching.